Okay, a few minutes later and refresh, we're ready for round 2. We did lowest order, now let's do next to lowest order. So last time we talked about the QCD Feynman rules, how they lead to the negative beta function. That negative beta function is what makes QCD a fantastic template for your favorite grand unified theory, whatever it might be, because QCD is our only UV complete theory that we know, at least the only one that we know exists so far. So let me say the non-abelian theories like QCD are our only example of UV complete theories. So there's no accident that one of the candidates for beyond the standard model physics is called Technicolor. It's basically just the hypothesis that what if something like the quark is not a fundamental particle? What if it's a bound state exactly like the proton and it's held together by a force kind of like QCD? That is again a non-abelian UV complete theory. So it could be turtles all the way down of protons inside of protons inside of protons with whatever level of complexity that you want. But whatever your UV complete theory of nature is, it's going to have a lot in common with QCD by default. We talked about 2 different limits of high energy scattering. Regi kinematics, the limit when the center of mass energy is much greater than the momentum transfer. In DIS language, this is equivalent to saying that the photon invariant mass W squared is much larger than Q squared. So this is the limit where Bjorken X is Q squared over W squared, which is small. None of this makes sense to you, by the way, if you don't already know about DIS, because I haven't told you, but just as a way of context for those who do. In contrast, for Bjorken kinematics, this is the limit where S and T are both comparably large together. That's the limit where Bjorken X is Q squared over W squared plus Q squared, and that could be any number of order 1. It doesn't have to be particularly small. So Regi kinematics, where it's forward scattering dominated, is synonymous with small x. Bjorken kinematics, what we normally talk about for DIS, where you're interested in large angle scatterings. The last thing that we talked about was a direct calculation of the elastic quark-quark scattering cross-section in Regi kinematics. The answer that we got was an expression for sigma dt. The Mandelstam t was that p perp squared. It was proportional to alpha s squared. It was proportional to the color factor, and it was independent of s as s goes to infinity. So it was constant and unsuppressed in Regi kinematics. And that's in contrast to the exchange of other kinds of particles. If you exchange a particle with spin lower than 1, you end up with a cross-section that is further and further suppressed with increasing energy. So gluons or vector bosons more general dominate Regi scattering. Okay, the next thing that I would like to do is now calculate the first radiative correction to this process. So I'm interested now in Regi scattering of 2 quarks off of each other where the final state contains quark, quark, and 1 gluon. So the scattering process is made up of 5 diagrams at lowest order. I could produce that extra gluon radiation in sort of 4 standard ways. You could have it emitted as final state radiation. These are these diagrams A and C. I could have final state radiation off of the projectile or final state radiation off of the target. Likewise, I can have initial state radiation off the projectile or initial state radiation off the target. All of this is also true for QED. I could have photon exchange and photon Bremsstrahlung. The part that's totally new and unique to QCD is this one, where the T-channel gluon itself undergoes Bremsstrahlung. And part of what we're going to do here is a detailed calculation, at the rate things are going, probably only of diagram A, and then we will infer the answer for diagram B. We will happily get diagrams C and D for free by reflection symmetry from diagrams A and B, and then I will wave some hands and give you for free the answer to diagram E. Any questions before we dive on into the next calculation? Yes, ma'am.
With UV completeness, this idea of like that momentum, the data becomes small.
That's right. The asymptotic freedom is what makes QCD a UV complete theory. UV completeness means well-defined theory up to infinite energy. It does not break down necessarily just because the energy gets large. So the idea is whatever your fundamental theory of nature is, it is well-defined up to infinite energy scales. That is the true high energy theory of nature. Okay, so before we roll up the sleeves and start calculating all of these terrifying amplitudes, let me introduce a particularly helpful convention for the momenta. I meant to do this in the last lecture, but I was so excited about calculating the cross-section that I skipped it. You may or may not be familiar with what are referred to as light front or light cone components. light front, also known as light cone coordinates or components of a vector. It's a really simple just change of variables. I define p plus or p minus to be 1 over the square root of 2 p0 plus or minus p3. All I'm really doing is just rotating my p0 and p3 axes. My usual space-time diagram has the time-like component up here, the space-like component on the horizontal axis. All I've done by defining these rotated coordinates is change those axes. So the p plus axis is the one which goes symmetrically along the time-like and the space-like direction. The p minus axis is the conjugate axis which goes in the other direction. Why do I care? Why is this useful? Because particles which are light-like, traveling at the speed of light, travel along a trajectory pointing along p plus. So it's very helpful to describe high energy scattering in terms of a particle moving with an enormous p plus momentum that's going at the speed of light along the positive z-axis. And by construction, a particle with large p plus has small p minus, and vice versa. So these are especially useful for high energy scattering. And I should be really clear here. This is not the same thing as light front quantization. That is a completely different beast with its own pitfalls and dangers. Not the same as light front quantization. This is just a choice of basis for your vector components. You're free to do that however you like without screwing up how you quantize the theory. Okay, why is this useful? So for one thing, let me re-express the dot product of two vectors in terms of these components. If I just perform the change of variables from p0 and p3 to p plus and p minus, then the dot product looks like p plus q minus plus p minus q plus minus p perp dot q perp. You have this interesting kind of funny off-diagonal contribution in the light front components. That means basically that your metric tensor in terms of plus minus xy is off-diagonal in this form. This also means, by the way, that if I have a vector component which is upper p plus, that's the same thing as lower p minus, because if I scramble up these components, that's how I raise and lower the indices for the metric. So p upper plus is the same as p lower minus and vice versa. I'm going to stick away from putting any of these indices downstairs. I'll always move them upstairs so that I have combinations of p plus q minus limits. The light front components are very helpful for describing an on-shell particle moving at high energies. So if I have an on-shell particle, that means p squared equals m squared is supposed to be a constant. And that p squared, according to light front components, is 2p plus p minus p perp squared. And this basically lets me solve for one of the p plus or p minus in terms of the other. So for instance, I could fix the value of p plus, and then I know p minus is equal to p perp squared plus m squared over 2p plus. And this is helpful because, as you sort of anticipated from this diagram, if p plus is getting large, p minus is getting small. As p plus goes to infinity, the energy moving along the light-like axis p plus gets big, the amount of energy moving along the light-like component p minus gets small. So it's a very helpful way of separating out your large and small momentum scales when dealing with high energy scattering. And we'll definitely take advantage of that now for calculating this diagram A. Okay, any questions before we start applying the Feynman rules? Okay. All right, so I want to consider the scattering. Let me draw diagram A for concreteness. Oh yeah, I don't need to draw it on the board because I already drew it in. Okay, so let me set up this diagram in an analogous way to how we set up the elastic scattering at lowest order. I've got P1 coming in, P2 coming in. Those are the projectile and the target respectively. Now I'm producing an extra particle in the final state. So now I've got an extra momentum K, and I can't just call everything Mandelstam, ST, and U. There's more momenta in the game, and I've just got to deal with it. So in addition to P1 and P2, I have the momentum transfer, which now I've called Q. I've chosen it to flow down, and I've called the momentum of the produced gluon K. So first order of business is let's specify the kinematics. I have high energy particles P1 and P2 coming in, they're on shell. I have high energy particles P1 prime, P2 prime, and K coming out. Those are also on shell. Let me choose a particular frame of reference for this. That way I know which is my large component and which is my small component. So I'm going to choose my frame of reference such that the large light front plus momentum is down here on the bottom. The large light front minus momentum is up here on top. So I'm going to choose that P2 minus coming in to be the large component. And I'm going to choose that the P2 plus and the P1 minus are the large components in this problem. This is basically saying I've chosen my coordinate axes such that the particle P1 is moving along the light front minus axis, and that's colliding with particle P2 coming in along the light front plus axis. So of course, I'm always allowed to do this. This is just a choice of reference frame. So as we just talked about, if I know that these are on-shell particles, then I can write my P1 mu, which has a large minus component, as whatever its minus component is, P1 minus. I choose my frame such that it has zero transverse momentum coming. That is, I'm in a collinear frame to P1 and P2. So the center of mass frame is one example of this kind of thing, but it doesn't have to be exactly the center of mass. Once I specify P perp and P minus, that automatically fixes P plus by the on-shell conditions to be m squared over 2 P1 minus. Likewise, I have P2 mu. P2 mu is coming in with a large P2 plus component. It also has zero transverse momentum. And by on-shell conditions, its minus component is m squared over 2 P2 plus. And now if I close my eyes and don't think too much about how I'm violating my on-shell conditions, I can take P plus, P2 plus and P1 minus to infinity and write this as 0 P1 minus 0 perp, P2 plus 0 minus 0. So this is the massless approximation. The exact kinematics are this, keeping the mass. This is the one that prevents it from being exactly light-light. But clearly, if I take P minus to infinity, this one is going to 0, so it becomes light-light. And this is what the light-light momentum looks like. So this is just a way of separating out the large light-light momenta coming in along these different directions. Now, I can choose the kinematics of the scattering. I can also choose the kinematics I want to look at for the produced gluon. So I have a large P plus momentum down here, a large P minus momentum up there, and now I've got to decide where does the gluon go. The gluon could go forward to the minus going direction. It could go down the beam pipe along the negative z-axis. Or it could go down the beam pipe along the positive z-axis. The case that I'm interested in is when it comes down right in the middle. So not at forward rapidity, not at backward rapidity, but at mid rapidity. Mid rapidity is the case where this gluon is being produced with a plus momentum that is negligibly small compared to the big plus, and a minus momentum that's negligibly small compared to the big minus momentum. So the region of gluon momenta that I'm interested in is the mid rapidity production region. I want K plus negligibly small compared to the big plus momentum P2 plus. But it can't go all the way to 0. It's still got to at least be big enough that I don't screw up the other things that I called 0. It still needs to be much larger than the tiniest plus component, which is P1's plus component. Similarly, I need K minus to be much smaller than P1 minus, and I need that to be much larger than the tiniest minus component, which is P2 minus. This is my region of validity of the approximations that I'm going to need to use to do the calculation. Why do I say mid-rapidity? The definition of the rapidity is 1/2 times the logarithm of K plus over K minus. It's very convenient to write in lifelong coordinates. Yes, sir.
Should in the Massless approximation,
Yes.
should the first 0 be 0 plus?
Oh, yes, thank you. Yes. I just try to do that to keep track of which component is which. Thank you. Right, so why do I say mid-rapidity here? The larger the plus component and the smaller the minus component, the larger the rapidity, and vice versa. The rapidity is a logarithmic variable that basically on these light front axes, y equals plus infinity describes the light direction along the plus z-axis. Y equals minus infinity describes the light direction along the minus z-axis. And I'm talking about particle production right in the middle, not going down the beam pipe this way, not going down the beam pipe that way, but smack dab in the middle of your solenoidal tracker, where you have all of that nice particle. So this is mid-rapidity particle production, and you can literally get this in terms of the rapidity variable y. Okay, one other comment about x. This is a different x, which is maybe not obviously related to the x we were talking about a little while ago. The plus momentum here, being small in comparison to the big plus momentum in the problem, can be written as a momentum fraction, which is often called Feynman x. This is K plus over P2 plus, and the region that I'm looking in is the region where that is much less than 1. This is the x of this gluon compared to the targets. You might, depending on your purposes, you might define an x1, which is the fraction of minus momentum compared to this. That's also small. This one is the fraction of plus momentum compared to this. That's also small. Mid-rapidity is nice because both the plus and minus components are small compared to the light-long axes. This is Feynman x. Feynman x is not the same thing as Bjorken x. Not exactly the same thing, but they are very closely related. Okay, I think I've probably said enough about the kinematics at this point. That specifies the incoming momenta. I now specify the outgoing gluon. The gluon is on shell. It's also massless. The gluon has some transverse momentum, and it has some K plus. On-shell condition fixes K minus to be K perp squared over 2K plus. This is not necessarily going to 0. K plus doesn't have to go to infinity, just because P plus does. K plus is much smaller than that. So here I have to keep all of the components. Those are non-trivial. Let me work out the on-shell conditions for Q mu, because that's maybe not obvious. Q is not one of the external particles. Q is the one being exchanged. So the on-shell conditions that fix the components of Q actually come from Q's role in the external particles that know about Q. So I need to use the on-shell condition for that particle and the on-shell condition for the other final state quark. So I can use those to fix the values of, let's say, Q minus. The value of Q minus is fixed by the on-shell conditions of the lower part of the diagram that has a large P plus. So I can get this from P2 plus Q's minus component, as long as I take away P2's minus component. P2 plus Q satisfies the on-shell condition, so that is Q perp squared plus M squared over 2 P2 plus Q plus minus, and then P2 minus was itself M squared over 2 P2 plus. And if I just stare at it for a second and say P2 plus is going to infinity, that one I can drop, which is effectively setting this to 0, which we said before. I ignore Q plus in comparison to P2 plus. This is also quite small. P2 minus, P2 plus is the large component. Yeah, that's right. Let me not set this to 0 too quickly. Q perp squared over 2 P2 plus. I think I could get away with calling this 0. I don't think I actually need the finite value for the rest of the calculation, but let me keep an eye on it for now. So this sets the value of Q minus from the on-shell conditions of the outgoing quark and the incoming quark. Similarly, I set the value for Q plus from the on-shell conditions from the incoming and outgoing quark on the top half. So Q plus I can get from P1 plus minus K plus minus P1 minus K minus Q. I think I've got it correctly what's written up there. P1 minus K minus Q, and then I add and subtract the necessary momentum that this gives me back Q plus. P1 plus is m squared over 2P1 minus. K plus is not particularly small. And this one is m squared plus K plus Q perp squared over 2 P1 plus minus K plus minus Q plus. And again, these things are negligible compared to, minus. The large minus component here. This overall thing goes to 0 as P minus goes to infinity. This also goes to 0, so the dominant contribution is this one. So I get Q plus is approximately equal to negative K plus. So this is basically a way of telling you how the large momenta are flowing through the diagram. The easiest thing is if the large plus momentum just goes straight down the beam pipe. You pay a penalty every time you want to send some of that momentum through the T channel. This construction basically sends the minimum amount of plus momentum up through that gluon just to give you the kinematics you need for that emitted gluon in the final state. Okay, so that's how we fix the overall kinematics. Why am I belaboring the kinematics so much? Because the kinematic differences between diagram A and diagram B give the entire effect. We'll follow through how this actually works at the level of the Feynman rules in a minute, but the essential difference just comes from the kinematics of the intermediate state propagators. In diagram A, the intermediate state is that P1 minus Q. In diagram B, it's P1 minus K. Let's calculate what those are. So P1 minus Q squared. This is the one for diagram A. If I expand out that square in light front components, that's P1 plus minus Q plus, P1 minus minus Q minus P1 perp minus Q perp squared. Let's see, P1 minus is the huge one, so I forget about Q minus in comparison to the giant P minus. P plus is tiny. How tiny is Q plus? Q plus is also pretty tiny. Let's see, so my P plus I took to be 0, my Q plus I have Q perp squared over 2 P plus. P2 plus. P perp was 0 by frame choice. So this just gives me 2, I have negative Q perp squared over 2 P2 plus. I have sorry. I'll look something here, 1 second. This is the minus. Oh, okay. I'm plugging in things in the wrong place. Sorry. Right, so by frame choice, P1 perp is 0, so this is just minus Q perp squared. I set the Q minus to 0 in comparison with the P1 minus. My P1 plus is tiny, my Q plus, however, is not tiny. Q plus is negative K plus. So this is positive K plus here. And I end up with 2K plus P1 minus minus Q perp squared, and if P1 minus is going to infinity, I can ignore this term in comparison to it. Right, this is the large scale. So I have 2K plus P1 minus is my evaluation of that virtuality. This is the off-shellness of this part. So similarly, I can do the calculation for diagram B. That's P1 minus K squared. So I get 2 P1 plus minus K plus, P1 minus minus K minus, again, only K has transverse momentum here. P1 minus is huge, so I ignore K minus in comparison. P1 plus is small, so I ignore that in comparison. And my K plus is just, it's just K plus. So I get minus 2 K plus P1 minus K per squared. And for the same reason, this is something finite. This is going to infinity, so I ignore it. The leading contribution is minus 2 K plus P1 minus. So we'll propagate this through the Feynman diagrams in a minute, but the essence of what's going to happen is already contained here. The kinematics of the scattering, the high energy kinematics, are identical for diagram A and diagram B with one difference. That one difference is the sign change of that intermediate state going from something positive, meaning time lag. That's the one where the momentum is all flowing together. The plus and minus momentum are flowing parallel to each other in that propagator, giving you something positive. Whereas in diagram B, they're flowing against each other. This one was final state radiation, this one is initial state radiation, and that's exactly the reason for that minus sign in between. Okay, to whatever extent we have time for, let's plug some things in Feynman rules. How are we doing on time? Half an hour? Okay. Okay, so let's evaluate diagram A in detail. All right, so starting with the upper line, I have an outgoing spinner. Let me call that U bar 1 prime just for simplicity, the same way we did before. The first thing that encounters now is the gluon emission vertex coming from the final state interactions. So this is now the vertex IG epsilon / lambda star TA. Lambda is the polarization of the outgoing gluon, A is the color of the outgoing gluon. I'm not done yet. After emitting the gluon, or before emitting the gluon, but after in the expression I'm going to write, now I have the intermediate state propagator. So that is P1 / minus Q / over P1 minus Q squared. Now I have the interaction vertex of the T-channel gluon. This is another IG gamma mu TB, and then I end with U1. So that's the product along the upper line. I also have a product along the lower line. I have U bar 2 prime IG gamma mu. Let me call it gamma mu prime so I can write the propagator. TB prime U2. This is essentially the same as what we had before for the elastic quark scattering calculation. And then I also have the gluon propagator in Feynman gauge, which is minus I G mu prime in this notation, delta B prime divided by Q squared. Yes, I didn't write it here, but you can also do quickly the other calculation. Your Q squared is just dominated by that minus Q per squared. You can sort of already see it here. Yeah, since your K plus is small compared to the P2 plus, when I square Q, this product, the P plus, P minus is small, the transverse component dominates. Okay, so I can clean this up.
Can I ask you a question?
Sure.
In the top line, it's IG.
Yes. So I sort of took a shortcut here. What I should have done was call this gamma alpha or something, and then I should have had an extra part of the Feynman rule for epsilon lambda star alpha in the final state. This is the outgoing polarization vector for the gluon. And I just took a shortcut by immediately turning it into a slash inside the trace. Sure, no problem. Okay, so if I simplify the expression, I get IG cubed divided by Q perp squared 2K plus P1 minus. I have TA, TB, I prime I, TB, J prime J. I didn't carefully spell out the color indices here. If I had, then I would have said this is TA, I prime, I double prime. I prime is the final color. This is some intermediate color. On that same upper line, this TB is I double prime I. So when I combine the two together, I get I prime I overall, but with both color rotations in this order. On the lower half, I just have TB. And then the spinner part still remains. I have U bar 1 prime epsilon slash lambda star P1 slash minus Q slash gamma mu U1 U2 prime gamma mu U2. So I could proceed now the same way that we did before. I could calculate diagram A, diagram B, laboriously calculate all of the other ones, then square it and get all of the terrible interferences among the 5 squared terms. Much advantageous, however, if I can, to work at the amplitude level. Let me simplify this as much as I can now using Eikenel kinematics at the amplitude level before I add everything up. How do I do that? It's not always simple to evaluate things at the amplitude level. But I'm really helped here by these Eikenel kinematics. By the way, I think I started using this word without defining it. The Eikenel approximation is synonymous with Regi kinematics. This is again just another S going to infinity. Let's say in this case P plus going to infinity, P2 plus going to infinity with I don't know, P2 perp fixed. You could do the same thing with plus or with minus. It's the same way of saying I have huge amount of momentum along the light-like directions, tiny everything else. The Eikenel approximation is the expansion in powers of S, essentially, so that I pick up the leading behavior as S goes to infinity, and you can think of it as a series where there can be power corrections in S beyond what we keep here. So if I say Eikenel, this is what I'm talking about. So how do I evaluate this thing at the amplitude level? Well, one thing that I can do is I can really simplify that spinner product on the lower half of the diagram. That's because that spinner product is a U bar of P2 prime gamma mu U of P2. And you know, yes, P2 and P2 prime are in fact different from each other, but they're not very different from each other. They have the same leading component. They have the same large P2 plus. So this matrix element is almost the same thing as U bar of just P2's plus component, gamma mu, and the same P2 plus. The fact that I can approximate this as having the same momentum on both sides means that I can evaluate it using a pretty simple version of the Gordon identity. The Gordon identity tells me how to evaluate in general a product like this, the U bar of P gamma U of P prime. There's 2 terms in the Gordon identity. There's some other messy stuff that comes from the difference of P2 and P2 prime. But for the case where they're equal, it's really simple. You just get a factor of 2 times whatever momentum you have. Right, so the Gordon identity, as I'm going to be using it, is U bar of P gamma mu U of P equals 2 P mu. And if I even put down spins, I could have different spins. This expression, as long as the momentum of the is the same, is diagonal spin. Spin independent. So this is going to give me just the plus component, the large one, 2 P2 plus. I only get this if my mu is the correct vector index to give me plus for the answer. So I have to have a Kronecker delta that sets mu equal to plus. And I trivially get a delta of spins, S2, S2 prime. So once I can approximate, Eikenalize the lower vertex, now I know mu equals plus. Mu equals plus. And that helps me over here. Now I can plug this in, and I have gamma lower plus technically And I don't like lower indices, so I'm going to immediately turn that into gamma upper minus.
What does it mean for me to be plus or minus?
It's just a component of the vector. So just like you could have, PZ or P0 or something, these are the P plus or P minus vector directions of the momentum. Okay, so we've evaluated U bar of P2 prime gamma mu, U of P2 is approximately 2 P2 plus delta mu plus delta S2 S2 prime.
Recording stopped.
Now
Recording in progress.
Now I should work on the other matrix element, U bar 1 prime epsilon slash star P1 minus Q slash, and now I know this is gamma minus, and I have U1. Okay, so now I know which gamma minus component enters here. That helps. The next thing that I can do is simplify this slash momentum. The largest momentum which enters in here is P1 minus. So the large component is P1 minus gamma plus. There's also Q minus, but Q minus is negligible compared to gamma plus. If I had something different than gamma plus, if I had gamma minus, for instance, that would come together with things like P1 plus, but P1 plus is tiny. So just by doing the power counting in terms of the large and small momenta, I can pick out the dominant gamma structure of this term. And that's really nice because I can pull this outside. And now I get P1 minus as a multiplicative factor out front, U bar 1 prime, epsilon slash star, gamma plus, gamma minus, U1. Now I can take advantage of the equation of motion, the Dirac equation. The Dirac equation in the massless limit says P1 slash acting on U1 is equal to 0. Usually there's a P slash minus M, but I'm working in the massless limit, so I don't care. Similarly, if P1 is dominated by P1 minus, this statement is P1 minus times gamma plus times U1 equals 0. P1 minus is just a number. You can divide it out. This tells you gamma plus times U1 is equal to 0 with the light-like kinematics of the Dirac equation. That means if I take these two gamma matrices and I anti-commute that gamma plus over, I get 0. So I can, for free, replace it by the anti-commutator because the term that I'm adding to switch the order is 0. That anti-commutator is just 2g plus minus, which is just the number 2. So now I've killed 2 of the gamma matrices, and I just get a factor of 2 for my time. So I get U bar 1 prime epsilon slash star. Now I've got P1 minus in front and a factor of 2, and I just get U1 left over. And this is now again of the form that I can use the Gordon identity for. The epsilon is just another constant. This is 2P1 minus epsilon lambda star mu U bar 1 prime gamma mu U1. And if I use the Gordon identity to evaluate the large momentum on that line, this is just 2P1 minus delta mu lower minus delta S1, S1 prime. So I have overall 2P1 minus squared, and then I have epsilon lambda star, just the particular component with lower minus, but I hate that, so I'm going to turn it into upper plus. And then trivially delta functions for the spins. So the Eikenhoff kinematics, high energy scattering, helps you a lot to work at the amplitude level and simplify these things down. I would not want to try to evaluate spinor traces or spinor products for general kinematics, but for high energy kinematics, it's not so bad. Time check, how are we doing?
5 minutes more, we'll say?
5 minutes more. Okay, then.
10 minutes.
Either way, it's time to start showing answers and doing less algebra. Okay, so we have all of the ingredients now. If I plug it all back in, my final answer is INA is IG cubed 2S over Q perp squared epsilon lambda star, just the upper plus component divided by K plus. And then I have my color factors, TA, TB, I prime I, TB, J prime J. And then simple Kronecker deltas for the spins. Okay, this is the answer for that diagram A with the final state interactions. The calculation for diagram B goes exactly the same way, and it's only different in a couple of respects. Those only differences come from the intermediate state, that P1 minus K, which in the Untitled approximation generates a minus sign. The thing that was 2P plus or 2K plus P1 minus before is now negative 2K plus P1 minus. So I'm going to get an overall minus sign here. And I have the fact that now those gluons are interacting in the opposite order. So the thing that was over here, first TA for the final state gluon, then TB for the scattering, is now first TB for the scattering, then TA for the emission. Because this is an initial state radiation, this is a final state radiation. So the only differences between these two diagrams are a minus sign and TBTA instead of TAT. And this is already enough to allow us to draw very substantial conclusions about this process. Let me see what I have on the next slide. Oh, good. I have the answer and I've highlighted how they're different from each other. So these are the critical differences between them, and there's physics in this. This is telling you that high energy scattering has identical radiation for final state and initial state, but totally out of phase. So it's not like there's no emission. There is emission. Here it comes in with a positive sign. Here it comes in with a negative sign. But the direction of the incoming quark and the direction of the outgoing quark are identical to each other. The deflection angle is practically zero. So the radiation pattern here is sitting exactly on top of the radiation pattern there. And the only difference is a phase shift by pi from initial versus final state radiation. The other change that comes specifically from the non-abelian nature is the interchanging order of the color matrices. And this makes a huge difference. So just compare for a second, what does this mean if I have these amplitudes in QCD versus the same things in QED? So if I just add these two things together, MA plus MB, everything is the same. IG cubed 2S over Q perp squared. It's exactly the same kinematics. Epsilon star plus over K plus. And the only thing that's different is that now combining the minus sign and the difference in the order of the matrices, I get a commutator. This object is commutator of TA with TB, I prime I component, which is I, F, ABC, TC, I prime I. So this immediately tells you this combination is only non-zero for QCD. If you did this process for electrons in QED, you would still get the minus sign. The minus sign is kinematics, but you wouldn't have any color matrices. There would be no difference between this pattern and this pattern. And therefore, you would get perfect cancellation of initial state radiation and final state radiation in QED. And that makes perfect sense because everybody knows that to make an electron radiate, you have to make it accelerate. And if I have two electrons coming with infinite energy straight at each other and zero deflection angle, they didn't accelerate. So it's perfectly logical that in QED, there is no net power emitted in the form of photons. But in QCD, in any non-abelian theory, you have an internal degree of freedom. It's literally like, well, they didn't accelerate in kinematic space. They accelerated in color space. They rotated from one color to another. And because of that, they're different. So you couldn't be more clear. This is non-zero because the theory is not abelian. And if the theory is non-abelian, it will be non-zero. So this is a uniquely non-abelian effect. The high energy Regi kinematics are boring. They are trivial for QE, but they are exquisitely sensitive to non-abelian gauge theories like QCD. If we had more time, then we would go through and we would actually calculate the cross-section for this. Before I show you the answer for the cross-section, let me point out another nice feature of this result. When we had the commutator that came out of adding these two amplitudes produced the structure constants FABC. And that rings a bell. FABC is exactly the color structure that appears in the triple gluon vertex. So it's almost like I added up diagram A and diagram B, and I got a weird version of diagram E. And since A and B are mirrors of C and D, if I add up C and D, I will again get a contribution of the same form. So QCD conspires to not only give you something non-zero, but to unify A, B, C, and D into the form of diagram E. And you can literally write it as if it were a strange 3-gluon vertex with a Feynman rule you can write down. This is called the Lipatov vertex, and it's a gauge invariant expression of all of those diagrams combined. That is the essential building block for small x gluon radiation.
Quick question.
Yes, go ahead.
So diagram E really has some very nice symmetry to it. Is that why we like to think of these in terms of this basis? But I imagine that we could represent it using one of those other diagrams
You're saying,
hearing like that process.
You're saying diagram E is convenient by some choice? I don't think I understood.
I'm asking why is diagram E why is that one the one that seems to the generic diagram with our
Right.
point-like interaction? Why does that take the form of diagram E compared to the other ones? And is that related to the fact that E has this nice symmetry, whereas all the other ones are clearly antisymmetric in some way?
Yeah, I think that's essentially it, that the kinematics of A and B are identical but anti-symmetric because of that minus sign. And so that's sort of, it's not going to look like A by itself, it's going to look like the combination of A and B to be something symmetric. I think you've got it right.
Thank you.
Okay. Right. So if I skip all of the squaring of the amplitude and just go right to the answer. So the overall amplitude has the form minus G cubed F ABC TC I prime I TB J prime J 4S over Q perp squared epsilon lambda star mu times the combination of momenta K perp mu over K perp squared minus K plus Q perp squared over K minus, K plus Q per mu, K minus K plus Q per squared. Yes. So this combination of momenta entering in along with the FABC, this is the expression for the Lipatov vertex. You can sort of read off from this what the effective vertex is. Then you calculate the amplitude squared, and you get 8 G cubed CF S squared over Q perp squared, K perp squared, K plus Q perp squared. Very nice, and then you can get the fully differential cross section, d sigma, d2 K perp, d2 Q perp, dy, with y the rapidity of the emitted gluon, 2 alpha S cubed CF over pi squared, 1 over Q perp squared, 1 over K perp squared, 1 over K plus Q perp squared. Okay, so you get this nice answer. So what? The transverse momentum stuff is nice, it's clean, but it's very specific. This is very specific to the case of one quark scattering on another quark, where you get the sort of 1 over K perp to the 4th at large K perp, 1 over Q perp to the 4th at large Q perp. That's specific to the particular case of a quark scattering on a quark, which is not very realistic. Nature doesn't give us quark-quark scattering. That part will change if I make it, let's say, dipole-dipole scattering, which is something that would enter in light-by-light scattering processes. Or if I make it a realistic proton-proton scattering, that transverse momentum spectrum will change. The part that's robust, the part that I really care about on all of this, is actually the rapidity dependence, the dependence on the K plus. And if I look at everything on the right, with respect to that rapidity, this is just a constant. So forget about the transverse momentum stuff. That's going to be sensitive to the details of what system you're using. But soft gluon radiation in this mid-rapidity regime is independent of the rapidity. So you see explicitly that the cross-section is d sigma dy. Say you even integrate out the other momenta, you don't care about them. The rapidity dependence alone is just a constant. And that feature that describes particle production in QCD, it tells you high energy scattering radiates a uniform spectrum of soft gluons. As long as it's in the middle of the rapidity region, it doesn't matter what rapidity it is. And that generic prediction agrees fantastically well with experimental data on the rapidity dependence of particle production in high energy collisions. This is experimental data on inclusive hadrons in proton-proton goes to hadron plus X at CMS. And you see, as a function of pseudo-rapidity eta, the distribution of hadrons is practically a constant. It's not only a constant, it's almost a constant all the way up to the ends of the beam window, the beam rapidity. Detector acceptance cuts out here, but actual beam rapidity, I think, is like 5 units or so in each direction in this collision. So the prediction that we see from like tree level QCD is that you expect to get a uniform distribution of gluons everywhere in rapidity, in between the rapidity of the projectile and the rapidity of the target. So what does that do now for my total cross sections? Basically, what that gives us is, if I compare now my quark-quark goes to quark-quark glue, the radiated cross-section we just did, divided by quark-quark goes to quark-quark elastic cross-section that we did an hour ago. That ratio is down by a factor of alpha s, because in this process I had to radiate a gluon. But I also have to integrate over the range of rapidity that the gluon went out. So both of these are contributions to the inclusive cross-section. Quark-quark goes to quark-quark plus x. So I have integral of a constant from y1 to y2. This object is just y2 minus y1. And if you evaluate what that rapidity is, then this contribution from the NLO soft gluon radiation is alpha s log s over m squared, which puts us in a very interesting situation where the coupling constant is small. In principle, the probability to radiate a gluon is small, but it has a very large phase space because it's allowed to radiate gluons anywhere across the entire beam rapidity. So if you have a high enough energy collision with a high enough rapidity, that rapidity, which is literally a logarithm of the energy, starts to compete with the coupling constant itself. And in the regime where alpha s is much less than 1, but the logarithm of s is much greater than 1, such that the two of them are not small at all, when that happens, I have to resum these contributions. This means the NLO radiated correction is just as important as the leading order elastic cross-section. And 2 gluon emission, as long as they're all sequentially ordered to all be soft, will also be just as important as the lowest order. And n gluon emission is all equally important, as long as everybody was soft compared to the one that came before. That gives you the picture of your original quark starts radiating soft gluons, and its soft gluons start radiating more soft gluons. And when I sum that series, I get an infinite cascade of a huge number of gluons, all of which have smaller and smaller momentum fractions x than the one that came before it. The same thing happens inside the proton. If you measure the proton structure at large x, it looks like 3 quarks. But as you go down and down in x, you start to radiate gluons, which start to fill up the proton with color charge. And those gluons radiate more gluons and more gluons and more gluons, until suddenly you don't have space to put any more gluons. They start interacting with each other very strongly. And this drives QCD out of the perturbative low density regime and into a regime that looks like many body physics. it looks like condensed matter. Right? This is the regime of high density, high energy coherent scattering. And this is the phenomenon of gluon saturation that we are searching for. I'll end with the tantalizing plots. We see this experimentally. We see an absolute explosion of the gluon density as you go to small x, exactly as predicted by the boost invariant spectrum of QCD. We see that the structure function, which counts the total amount of charge inside the proton, is blowing up as you go to small x. And the question is, what happens in that small x region? What happens when my gluon density is already so high that I can't just gram off another gluon without thinking about it? That's the regime that leads to gluon saturation. And whatever time I can scrounge up tomorrow, I'll try to tell you about it. Thank you very much.
Questions for Matt?
Yes, sir.
So is this like when people talk about color last time?
That's exactly it. So technical terms that I should have mentioned, but I forgot to. The evolution equation that resums these leading logarithms is called DFKL. That stands for Bolitsky-Faden-Kurev-Ipatov. This is the one that produces an exponentially growing gluon density. The evolution equation in the high density regime has several names associated with it depending on how it's formulated. It's formulated as the Jim-Walk functional integral equation at a mean field level. It's the Bolitsky-Kopchegov equation. You also sometimes see it referred to as the Bolitsky hierarchy of operators. The effective theory in this region, like when you are deep in the saturation regime, that you have that equilibrium point between radiating more gluons and reabsorbing gluons. That's when you're in the effective theory of high densities. Effective theory, and that's what's called the CGC, the color glass condensate. It's the semi-classical effective theory where you're dominated by arbitrary number of gluons, but you still have a perturbative series with corrections to it. Other questions?
There was one over there.
Yes.
It seemed like you took when you showed the same plot, it seemed like you were taking a result from Quark scattering and applying it to person.
Yes, that's right.
Why is that okay?
Because if you do the same calculation for different projectile and different target, you get different transverse momentum dependence, but you get exactly the same rapidity dependence. So I could do another perturbative calculation where it's all controlled. Protons are too hard. Dipoles are much nicer. So I can imagine like J psi scattering essentially, where I've got a tiny quark dipole, so that I can use perturbation theory for that. Then I get different transverse momentum dependence, but exactly the same constancy with. And then I can take an arbitrary gluon distribution. I don't know what it is inside the nucleon, but I can calculate a radiative correction to it, and that radiative correction is always boost invariant. It's always, it essentially just comes from that light front wave function that I alluded to at the very beginning. This one building block already contains that rapidity independence. And so this ingredient going into any of the other calculations always yields that answer. Any other questions? Yes, sir.
Okay, so amongst all the Feynman diagrams you had, B and D happened before the collision.
Yes.
So then the fact that they are rapidity independent, it doesn't make sense.
B and D themselves are not rapidity independent, I don't think. It's only the sum of everything, right? There's this careful cancellation. Maybe I shouldn't speak too fast. Without looking back at the diagrams, maybe they are separately boosted invariant.
But they don't even happen, I mean, they happen before the collision, B
Sure.
and D. So then how are you saying it's not even in the mid-rapidity area?
Sure it is. You can have initial state radiation that happens before the collision vertex that just happens to come out at mid-rapidity. Right? Your incoming proton is radiating gluons everywhere the whole time. Right? Some of those come out at mid-rapidity. Your outgoing particles are also radiating gluons everywhere. I don't know. I don't understand why you say initial state radiation can't be in mid-rapidity.
So the detectors can also get the initial state gluon.
Yes. These are. You never know the difference, right? If you're doing your calculation and you want radiative corrections to it, you have to include both initial state radiation, final state radiation. They all contribute to your observable. They all have the ability to create particles that come out and land in your detector. It is a little bit weird to think about, how does the gluon coming out beforehand know what's going to happen later? But that's always present in quantum mechanics. That's a feature no matter which theory you're working in. Yes, ma'am.
the connection or difference between diamond X and the
Ooh, yeah, so that's a really good question. Bjorken X is an experimental measurement that you make in deep elastic scattering. Bjorken X is specifically Q squared divided by 2p dot q. So in a given experiment, you measure a certain energy of the scattered electron, a certain angle. A given measurement corresponds to a given value of Bjorken X. So Bjorken X is a property of the experiment. Feynman X is a property of the wave function. Feynman X is, let's say, k plus over p plus. That's the fraction of momentum of a particular particle inside the proton. The connection between them is the DIS handbag diagram. When you actually calculate this thing, the on-shell condition for that outgoing quark effectively gives you a delta function that gives you delta of x Feynman minus x Bjorken. So at leading power, leading order, like this, kinematics can be smeared. So it's not always as simple as x Feynman equals x Bjorken. But the idea is x Bjorken is a measurement, and the information contained in that measurement tells you about a snapshot of the wave function. You say, at this time, I hit something with x of 0.3. Oh, that must have been a valence quark carrying 1/3 of the proton momentum. Does that make sense? Yes, sir.
Is this X Feynman the same? I've seen C used in some textbooks as the sort of a priori momentum fraction.
Yes, depending on context. Sometimes C is used for something synonymous to X. For GPDs, it's used for skewness, which is related to X, but it's a difference in X's. So yes, in general, but be careful depending on context. Thank you. Sure.
Nachman X.
That is this X with a shift that comes from having a large mass. So if you're doing deeply virtual meson production, then your on-shell condition has an extra mass that enters that shift. So the relevant X has this Nachman variable shift from the mass. Or like in order to put a J psi or something on shell, you have to deliver a minimum amount of plus and minus momentum to supply its invariant mass. So that's what provides sort of an extra shift on top of that. I believe that's correct. It's a little outside that.
Well, in the DS context, you have to go to large X, and the psi is a shift in. So you measure x Bjorken, and this is equal to x Feynman, right? At large X is different. At large X, x Feynman is equal to the Nachman psi, which is a shift of x Bjorken of the observable one due to the mass of the target.
Yes.
But at high energy or small x Bjorken, who cares?
Oh, I see.
The energy, the W square essentially is much larger than the mass of the target, and then who cares about the target? Who cares
Okay.
about the
So it's still a mass shift, but it can come from different places. I'm familiar with it in the context of heavy vector resonance, but that makes sense. Thank you.
questions.
Yes, sir.
Yeah, in your calculation of the two diagram A and B, they actually meet the longitude and the polarization one. So can I say that they are just here for gauging variance because I can choose a gauge, say light cone gauge to the limit?
Oh, I'm glad you asked about light cone gauge. Let me jump back. Yes, maybe this is good enough. Which longitudinal polarization were you referring to? Certainly not the radiated gluon.
The two amplitudes for A and B,
Yes,
MA and MB.
yes.
Yeah, they're actually class.
Yeah, so exactly. So this was a comment that I would have made if I had more time. Yeah, so this happens just because of the radiation here is coming from what I call the projectile. So the projectile has a large minus momentum. So the particular component of epsilon that it couples to is epsilon plus. You get P minus epsilon plus. And you're exactly right. If I wanted to, I could choose a gauge, a light cone gauge, such that epsilon plus is 0. In that gauge, I have, you will get A and B both equal to 0. And what that means is instead, A and B are 0, and you've moved all of the radiation down into diagrams C and D. I would prefer to do it the other way around. I would prefer to choose light cone gauge A minus equal to 0, because then C and D are 0, A and B and E are the whole story, and we've already calculated A and B. But you're correct, you're completely correct about light cone gauge. That's a very useful strategic choice that you can make to simplify your life when doing a complicated calculation like this.